Yeah, thank you for your time attending this webinar. This is the second webinar of the OC3. And today we are very glad to have Dr. Janne Repschläger from Max Planck Institute for Chemistry as our speaker. First, I would introduce Janne very briefly. She's currently working in the climate geochemistry department at Max Planck Institute for Chemistry. Her current research interest is include the changes of the surface and deep water circulation at the interface between the subtropical to subpolar North Atlantic and in the Labrador Sea over the last glacial cycle. Janne has also been the chair of the OC3 steering committee since 2019. Okay, and the title of her talk today is Insights into Deglacial AMOC Changes. It's a summary of the pages OC3 stable isotope compilation data from the North Atlantic. Okay, with that, I will pass the torch to Janne. Thanks, Janne.
Yeah, thanks a lot for this nice introduction, Ning. Yeah, welcome to all of you to this talk. I'm really happy to see so many faces and also some older colleagues, not old in terms of old, but colleagues I haven't seen for quite a while. So it's really great to have you here in the talk. Yeah, today after Juan last time gave you an insight into our OC3 database compilation, I now want to give you an insight into the first data product we have, which is the paper, my paper from 2020, which I wrote with the co-authors named on this slide. And I'm really thankful for Ning and also for all the others helping on compiling the data and working on this manuscript. And I'm also very happy and I'm very glad and I'm very thankful to all authors in the community who share data on the data repositories as Pangea and NOAA, which we used to build our database on. So today I will focus on the Atlantic data set from the OC3 compilation and with a special focus on the North Atlantic. And I will show you that our new results, which indicate that there is the deep water formation of abyssal deep water in the North Atlantic during LGM, and there was an active deep water formation in the North Atlantic during Henry Stiller 1. And I will also discuss the controversy of deglacial deep water stratification changes during my talk. And though I guess all of you are experts in the circulation patterns in worldwide and in the oceans. This is just a short reminder. This is a famous Wally-Broker global conveyor belt. And in my talk, I will mainly focus on this North Atlantic side, but I also include data from the South Atlantic to see the entire water column changes in the Atlantic. Yeah, to just give you another update or reminder on the circulation in the North Atlantic, you see that we on modern times have two main deep water convection sites. One is in the Nordic seas. Here, Iceland, Scotland overflow water and Denmark Strait overflow water is produced that flows through the silts southward. Iceland, Scotland overflow water then propagates along the mid-Atlantic ridge, but a lot of volume is also flowing into the Western Basin and then flowing along Greenland, combining with the Denmark Strait overflow and then combining to Western North Atlantic deep water. It is overlain by Labrador seawater, which is slightly lighter and produced in the Labrador Sea and then evading the slightly shallower deep North Atlantic in the Western Basin, more pronounced than in the Eastern Basin. An additional water mass, which we shouldn't forget, is the Mediterranean overflow water, which enters the East Atlantic Basin through the Strait of Gibraltar and adds a lot of salinity to the deep ocean. It's a relatively warm water mass. It has about 11 degrees in nowadays, but it's also very saline. So it's having a similar, nearly similar densities as Labrador seawater. It's slightly lighter. So here you see a short transect through the East Atlantic Basin and the West Atlantic Basin. In modern times, I just show it here to have a comparison for our later slides show in the talk. You see in the East Atlantic Basin that we have the Iceland-Scotland overflow water, the East-North Atlantic deep water, the lower deep water, which is a derivative of the Atlantic bottom water, Antarctic bottom water, and the Antarctic intermediate water. And you see that the phosphate concentrations are slightly different from the West Atlantic Basin, which indicates that the Western Basin is slightly better ventilated than the East. And you see the Denmark Strait overflow water here and the West North Atlantic deep water and IW and AABW in addition. So how did that look like in the last glacial? That is one of the main questions we have since years. Here you see one of the, the early works of Santine et al., who reconstructed the deep water distribution in the North Atlantic Basin, or East Atlantic Basin, based on delta 33. And you nicely see the modern distribution of North Atlantic deep water that reaches far southward over the equator with very light, very heavy delta 33 values. Whereas during the LGM, the delta 33 values were relatively, this Tongue seems to be weaker and penetrating less southward than in modern times. These pictures from delta 33 values were the basis for the circulation patterns that have been proposed ever since, which says that during the modern times we have North Atlantic deep water that penetrates very deep into the North Atlantic and then wells up in the Southern Ocean, and the Antarctic bottom water has a second deep water overturning cell that is situated in the south. During the LGM, it is anticipated that the AABW penetrated all the way northward, and the cell is just getting larger, whereas the NADW shallowed. This view has been discussed since a while, and there has been very early work in the 2000 to 1998, 2002 that postulated that there was a North Atlantic deep water source in the Nordic seas that was generating brine waters and filling the East Atlantic Basin and at depth. Yeah, so this debate has been ongoing, though this picture is like the picture that is well known and mostly by most of the researchers also appreciated. And another, yeah, and newer results from Kegvin and Swift also showed that there seems to be a source of deep water in the North Atlantic that is filling the abyssal ocean, and also evidence from epsilon neodymium rises that indicates that we had a North Atlantic deep water source that contributed to the water mass in the abyssal ocean during the LGM. So the picture is more like we had two weak deep water cells and a fast overturning cell on top of it, instead of deep overturning that filled the entire ocean during the Holocene. So the question is, based on can we also see these pictures based on stable isotopes, or is it just a picture we see when we use epsilon neodymium and delta 33 in combination? So that's one of my main research questions I had when I started with the OC3 work. Yeah, another point that arises is if you look into the benthic delta 33 distribution over Henry's daily 1, you see that the delta 33 becomes even lighter in the North Atlantic during that time, and that was interpreted as to be a shutdown of AMOC during these times. Anyways, if you look into the data set of Claire Walbrook in 2011, you see that the delta 33 values were already rising. The delta 18O values were already starting to decrease over Heinrich 31, which and started in the North Atlantic. So there must have been some deep water formation here. And that also was something I showed in my paper in 2015, that there seems to be an active deep water source during Heinrich 31, but we couldn't put a finger on that. And therefore, the research question was, is there an active deep water formation during Heinrich 31 in the North Atlantic? Another thing that I think is also very important during the deglaciation is that we had a change in stratification. So this is from Atkins 2013, and the conceptual view is that the AABW got really cold and is cold and fresh nowadays, and the NADW is warm and saline. During the LGM, it is anticipated that the AABW not only was cold, but also very saline, whereas the NADW was relatively warmer and fresher and overlaying this water mass. So the question now is how to come from a status where you have a warm, fresh water mass in the upper ocean and a cold saline water mass in the deep ocean into the modern circulation back. And Atkins' idea and Atkins and co-authors' idea was that there was an abyssal warming in the South Atlantic to overrun this density changes. But nevertheless, I think in the North Atlantic, we still have this paradoxon how with fresh warm water that is less dense than underlying cold saline water sink down. And if you think of the deglaciation, we even see that the North Atlantic or the entire ocean is warming. So the surface water would get even warmer and we would have more fresh water. So indeed, it would be getting even fresher and warmer. And if this cold saline water would stay there, it would be really, really dense. So we would need a mechanism that brings down the fresh, warm, low density water into the abyssal ocean. So that will be the last part of my talk. So just to summarize the research questions, the first question is, was there a deep water source in the North Atlantic that for the abyssal deep water during the LGM? The second question is, was there a shutdown of deep water convection during Heinrich 31? And the third question is, which mechanism allowed the drawdown of warm, less saline waters into the abyssal deep ocean? Okay. So let's come to the database. So we compiled 109 data from 109 cores with more than 9,000 data points. The analysis we did was on Cibicidoides species only, because we wanted to make sure that we don't have any species-specific effects. We also didn't apply any vital effect corrections, so we back calculated everything to the original measurement data if they were reported with a correction. We updated and synchronized all age models using the Paleo Data View tool from Stefan Mulitza, and we used the INTCAL 13 database for the reservoir age corrections. We analyzed 6 time slices: late Holocene, early Holocene, Younger Dryas, Billing Allerhood, Heinrich 31, and last glacial maximum. And if you look into the dates, you will recognize that they are slightly different from what is usually anticipated, as we reduced like the duration of the events by a few hundred years, to make sure that we wouldn't have any age model uncertainties being displayed in the results. So in my talk, I mainly will focus on the LGM and Heinrich 1 time slice, but I also will give you a short insight into the younger times. Okay, so let's start. There's a source of deep water in the North Atlantic that helped to fill the abyssal deep ocean. And where was it? So this is a transect through the Western Atlantic Basin. And you see it here displayed from north to south and depth from top to bottom. And it's the delta 13.3 values and the delta 18.0 values for the LGM time slice. And you nicely see very well ventilated water mass in the North Atlantic that penetrated all the way down to about nearly 4,000 meter water depth. And it's underlined by a less ventilated water with low delta 13.3 values. The same water mass has relatively heavy delta 18.0 values, though it's not as heavy as the Southern Ocean. And there seems to be a slight evolution from heavy to lower to heavier values in the deep ocean. Nevertheless, it's not that easy to recognize that, but what we recognize if we add the updated benthic atmosphere 14C ventilation ages from Zhao et al., we see that the water mass in the Southern Ocean is far older than everything in the north, and then there's something which is even younger in sandwiched in between. So this makes us sure that the waters that are sitting here in the North Atlantic can't originate from the south, and it must have a source in the North Atlantic. And actually, our database has a very high spatial resolution, especially in the North Atlantic area. So what we did, we were trying to follow this. And what we first of all did, we tried to follow just the flow path of the North Atlantic deep water. So we started where the ISOW starts nowadays and then flows around the Reykjanes Ridge and back into the Western Atlantic Basin and then all the way southward along the continental margin. And you see that the picture becomes much clearer, and you see this lower delta 18.0 values here in that picture. Okay, if you now go into like snaps, which are also used in modern oceanography, we try to do a OSNAP transect here, which is this one here and that one. And we also did a transect over the Nordic seas to see whether this signal of a light delta, heavy delta 13.3 and light and delta 18.0 can be traced back to the north. And actually, it can't be traced back all the way into the Nordic seas, but it seems to sit somewhere here in the Labrador Sea. But it's only one data point, so we have to be really careful here. And it'd be nice to get some more data from that area to really confirm it. But I show this here to show you that this new data compilation has the strength to also do this really great regional transects and look into details of deep water protection. Yeah, we did the same transects at 55 degrees north and 10 degrees north. And what you nicely see is that there seems to be some cell of deep waters that is situated at the margin of the American continent. And I think this is really interesting because it brought me to the idea that probably the deep water flow is not like very wide, but might also be confined to certain areas in the deep ocean. And that made me painting this picture and this concept of the deep water being from the north, being more confined to the American continental margin, whereas the AABW would flow along the mid-Atlantic ridge. And this is also something that modern oceanographers see. And I was surprised that we could see something like that in the LGM. So this brings me to the conceptual idea of how deep water circulation works in the north, in the LGM, and I think we can say that this conceptual idea of AABW being very strong during LGM and penetrating all the way up to the north can be crossed out. We still have two different ideas of what could have happened. We could have a deep water convection that's similar, strong from the north and the south, either both strong or both weak. And I think we have evidence that it's rather this kind of circulation based on the very light delta 33 values, which are probably generated by mineralization of light carbon at depth. So to say something, we could confirm this picture with our data set now. And just to summarize the first part, we can see that the OC3 database can be used to address spatial and temporal changes in the Atlantic deepwater masses. We see this delta 33 depleted 18O enriched deepwater mass at 3,000 to 4,000 meter water depth between 50 and 20 degrees north during the LGM, which has benthic 14C ages younger than Southern Ocean, and delta 33 enrichment in the North Atlantic exclude a southern origin of this water mass. Potential origins of the deepwater are active deepwater formation in the Labrador Sea and Erminger Sea, and or remineralization of light carbon at depth due to this slow overturning circulation. But to be honest, we really need more data from the Erminger Sea, Labrador Sea area to confirm this picture. So let's go on with the Heinrich Stadio 1 there. So again, the question is, where's the shutdown of deepwater convection Heinrich Stadio 1? And the second question I would like to pose on this time slice is, which mechanism allowed the drawdown of warm, less saline waters into the abyssal ocean? So again, we'll start with transects from the East Atlantic basin and then go to the west and then go again into transects along the deepwater flow path. If you look at the East Atlantic basin, delta 33 values, which are displayed here. Red is high values, blue is low values again. Here's 40 south, here's 60 degrees north. And you nicely see that there's a well-ventilated water mass sitting in the Iceland basin, and towards the south it gets less good ventilated. The same water mass has delta 18O values that are quite light at the upper part, like into 2,000 meters water depth, and at depth it is quite heavy with 4.5 to 4 per mil. If you have a look into the Western Atlantic basin, it looks a bit different. You see again this very light, this heavy delta 33 values, which are penetrating all the way southward and down to about between 3,000 and 4,000 meter water depth. But you see a distinct signature of light delta 18O that is invading somewhere between 60 and 30, 40 degrees north. And to see this picture clearer and to see where it invades on the flow path of the ISOW of the North Atlantic deepwater, we looked into a flow path picture and plotted along the transect, along the flow path of the NADW. And you nicely see that this heavy delta 33 values come from the North Atlantic Iceland basin, like in Nordic seas. And then it gets lighter towards the south. And you have two different signatures in the delta 18O values. You see on the one hand the very heavy values, and then the light values that are mainly sitting somewhere here in this area. Based on the water mass we see today, we associated this different water mass with names. This is potentially Iceland, Scotland overflow water. We see Western North Atlantic deep water. We see lower North Atlantic deep water, and here in the south we see AABW as the Southern Ocean end member. If you now ask the question of where the light signature originates from, we investigated transects along the classical Labrador seawater outflow, which is somewhere here, and then which is this transect. And then we did a transect from west to east across the North Atlantic to see whether the light waters would originate from the Mediterranean. So if you look into the Labrador seawater distribution, you see very light signatures, especially somewhere here in the Labrador Sea. And if you see look into the west-east gradient, you see that there is the very light signature here in the on the continental slope of America, where the meltwater comes out of the Labrador Sea, but you also see very light values associated with the Mediterranean overflow. So we both could be origin for these light values or could contribute to the light values. So the question would be, and of course, what we saw was that there was an Iceland-Scotland overflow water that has like very heavy values, right? So what we try to do now is we try to sketch up different mechanisms for formation of the deep water. So for the Iceland-Scotland overflow deep water formation, which is looking at like modern, we thought that the North Atlantic current water was probably transported northwards underneath the sea ice and meltwater lands of the Heinrich 1 event. In the North Atlantic or in the Iceland Sea and Nordic seas, we would have a sea ice with also some polynyas, where we would have heat loss, and the water mass would cool down and could generate ISOW. It becomes a bit more complicated if you go to this area where we know that there is a slight delta 33, delta 18O values. So we have several mechanisms that could explain those. Mechanism A would be a strong cooling and downwelling of warm saline NaC waters just at the southern edge of the ice and meltwater lands. And there's actually evidence from Rashid and Boyle, the subpolar the transition between subpolar and polar North Atlantic from different planktonic species that show a very similar delta 18O value during Heinrich 31, which points to a destratification of the water column and is regarded as to be a deep water formation event. So this could be one mechanism that potentially would take place at the continental slope of America, for example. The other idea is a warm water polynya. This would mean that the NaC waters would get subducted underneath the sea ice, and their short-term openings in terms of warm polynyas would show up, and the water will cool down and also bring some of the meltwater down into the abyssal ocean as deep water, and thereby this meltwater lands would be eroded step by step until and in the end it would precondition an onset of AMOC. It's a mechanism that has been proposed by Krebs and Timmerman in 2002, I think. This could explain like the delta 18O and the delta 33 values in our sites. The last idea, which is a very, very old one, is the idea of brine rejection. Brine rejection would lead to the drawdown of the delta 18O signature of the meltwater without with the decoupling of the salinity signal. So you would have very saline waters that would have a very light delta 18O signature. This is known from the Southern Ocean, but the question is whether we would have that in the North Atlantic, because we would need this shelf area to generate those. And additionally, in the abyssal ocean, we have very in this intermediate ocean, we have relatively high delta 33 values, and usually brine water rejection is associated with very low delta 33 values. So this could actually be a mechanism to explain this abyssal deep water mass here, but probably not this one with a light delta 18O signature. Okay, last idea that would kind of combine all mechanisms or some of the mechanisms with each other is that the NAC gets subducted underneath the meltwater lands, where we have some deep water mixing and formation. We have the heat loss in the north, and then we have ISOW, and the ISOW then gets warmed on its way southward, and then this would not be a newly generated water mass, but just this water mass that would be warmed up. And this warming could either originate from the Mediterranean overflow, or we could also have adiabatic warming from just the NAC that is subducted, because it brings some amount of heat that could just go downwards and warm the deeper water masses. Okay. Again, as I said, we would need to have a mechanism that allows the drawdown of the light 18O signature into the abyssal ocean. So either we have to decouple the signal, as with brine water formation, or we have to warm the waters, or we have to decrease the source water salinity, or we have an increased influence of isotopically depleted meltwater. And what we did now is that we looked into the different surface water compositions and calculated mixing lines between the different water masses to evaluate whether it would be possible to get a water mass that is dense enough to sink down just by mixing meltwater with this meltwaters with NAC waters, right? So which amount of meltwater could you bring down with tropical waters, tropical saline waters, to still keep that 18O value that has this signature of 3.5 per mil and has a decent temperature. So what we did is actually I used different source water masses. So I have a source here, that's the tropical waters that are shown here in the upper part of the graph. Then we have meltwater from the Labrador Sea, which plots here in the temperature versus delta 18O calcium plot. Then we have Mediterranean overflow water here, and we have 3 different sites of subtropical and subpolar waters. This is Carlson, this is Repschläger, and this is the one from Thornelli. What we did in addition, we plotted the delta 18O values for the Western North Atlantic deep water from our database, and the Henning signature of ISOW, and the temperatures for bottom water in the North Atlantic during LGM and Henning study 1. It's an average from the data of Thornelli and the data from Skinner et al. And myself in the different time slices. So what we then did in addition, I have this fractionation lines for temperatures of the delta 18O value that you would reach when you cool down the waters, and which if you cool down the waters, which delta 18O calcite value you would get in the foraminifer. Okay, if we apply a mixing of 50% tropical waters and 50% melt waters and cool it down to the temperatures we observe, we would end up somewhere here in this range, which is the Henning 1 bottom water temperature and the North Atlantic deep water we see here. So we could easily just get the signature by mixing tropical waters, Henning 1 melt waters 50-50, and get the melt water. This would argue for this deep water convection process at the southern edge of the meltwater lands. If we would apply a mixing of 75% tropical waters and 25% of meltwater, which is relatively, I think, more likely. 75 and then 25% meltwater, you would, and cool that down, you would end up at Iceland, Scotland overflow water. If you would even further cool it, you could also have the Iceland, Scotland overflow water just warm by 2 degrees here, and you would also end up in the same range of temperature and isotopic signature that we observe here. So actually, this diagram shows that both ideas would be feasible. One is the mixing 50-50% mixing of tropical waters and meltwater to generate this deep water, and the other one would be we could have a Iceland Scotland overflow water that is warmed on its way southward and also generates this deglacial signature. Okay, the last thing we tested on this was to investigate whether this water masses would still be dense enough to sink down. And here is the range of the 50-50% mixture, and you see that there's a high uncertainty in the calculations. And this is for the 25-75% mixture. And you see for both that it is likely to have this mixture going into deep water convection, become from glacial to modern. Though it's this 50-50% mixture, it seems to be slightly more likely. So our conclusion is that we have an invasion of delta 33 enriched 18O depleted North Atlantic source deep water between 1,000 and 4,000 meter water depth between 30 and 60 degrees north during Henry Stellium 1, with benthic 14C ages younger than the Southern Ocean. Oh, wait. We have an active deep water convection in Western North Atlantic Basin during Henry Stellium 1. And the depleted water starts to invade the deep ocean during Henry Stellium 1. The mixing of the subtropical waters and the Henry 1 meltwaters and abyssal warming by diabatic warming can account for the observed changes without decoupling of the deglacial signature from salinity and temperature, which indicates that we don't need any brine water effect to generate this signature. If you now have just a short look into the deglacial, here you see the Henry Stellium 1, younger dry, Berling Allerhut, younger dryas, and late Holocene delta 18O values. I didn't use the 33 anymore. And you nicely see this light delta 18O signature invading into the deep ocean during Henry Stellium 1, and then it gets further mixed southward during Berling Allerhut. During younger dryas, it gets even more mixed, and during the late Holocene, you see that everything is mixed into the deep ocean. This makes me think, or indicates that we really need this stratification changes in the Henry Stellium 1 to get the process of deep water stratification change activated during the deglaciation. Yeah, so I already showed this. This is my concept for the LGM, where you have a big abyssal deep ocean circulation fueled from the north and from the south, with little differences in the total volume, but both slowed down. And then you have this conceptual idea of having North Atlantic deep water formation during Henry Stellium 1, just by mixing of very saline waters from the tropics and very cold and fresh waters from the meltwaters. We have Iceland Scotland overflow water, North Atlantic deep water formation in Denmark Strait, and probably we also see some diabatic warming of the deep water masses during Henry Stellium 1. And this also could be associated with slower advection rates that would allow for more vertical convection. But I think this is something we also can discuss with the protactinium thorium people, because you have the data for deep water current speed during that time. And I think it would be very interesting to test different models by just using this additional data. Yeah, so just to give you an outlook, currently we are still increasing the resolution, or we're nearly done with increasing the resolution of the OC3 database. We could imagine to add some plantic data, which also has been done by Stefan recently. We thought of adding some other proxies. We are currently working on the publication of the other ocean basins, and of course, it would be great to compare our data with the other proxies like Protactinium thorium, which is an ongoing cooperation with Finn Züfke, and Epsilon Neodymium data we compared with Patrick Blaser. And additionally, I'm working on a project investigating the potential formation of Deepwater in the Labrador Sea, and yeah, reconstructing also Deepwater temperature and salinity changes. Yeah, with this, I would like to thank you for your attention and looking forward to your questions.
Okay, thank you, Janne. Thanks for the nice talk. Anyone have any questions? There is a comment. Okay, right.
Actually,
yeah, that was me in the section plots. I couldn't identify the dots for each sample or for each core, and I think that when we start like doing interpolation, it is important to show them just to.
You mean here? Yeah, actually, it's difficult to see, but we actually put them in the color of the.
Oh right, now I see. Sorry.
Yeah.
In the paper,
Okay.
actually, I have a
I think for
circle.
this plot.
Yeah.
Most of the plots you have, actually.
Okay.
Here
Sorry,
we have
I
like
couldn't
the
see
circles
them.
in a different, and I think here we have black circles around it, so you can better identify it.
Yeah.
Yeah, I think in the beginning it is unpublished data.
Yep.
That's the reason why it's not as polished. Yeah. Any other questions?
Yeah, you can directly unmute yourself and speak.
So Janne, how confident are you in pinpointing the end of Heinrich Stadial 1 exactly at 14.8? Because 100 years later, you are already in the billing, right? When you look at the ice cores. So
yeah, it's.
Do you think that some of the age uncertainty might lead to that include some of the billing samples into your Heinrich 1 reconstruction, or are you confident that this is not the case?
I'm highly confident that it is not the case, or even if it's the case, I'm highly confident that we still see a signature that starts on Heinrich event 1, and I think I can show you the reason. I have it in my introduction, fortunately. So you see that the delta 18O values in the North Atlantic, and this is the core from the here from the Iberian margin, already start to rise decrease during during Heinrich Stadial 1, and I also see it in my cores in the North in the Azores region. So this is a consistent signal in the benthic data, independently on H models, because this rise starts before the change in the carbon isotope change.
Yes, that's clear, but where would you put the end based on the oxygen isotopes, the end of Heinrich Stadial 1 in this? For me, it's right? Difficult. I mean, maybe on the basis of the carbon isotopes, but
yeah.
Just
I see your point, but it didn't really change the picture that much, because we'd still, even if you would put this point like to 15, you would still have this rise here, right? At this decrease, right?
Yeah, you have this decrease, but I mean it's a transient state, so it's very difficult always to calculate an average for Henry stadium 1 because it depends always how are your data distributed within this time interval.
I can even go further. I could say if I put it further to the left-hand side, like to the younger part, then I would even see a bigger signal. I guess so.
Yep.
Yeah, so I'm pretty confident that we see a real signal here. Yeah.
Okay, do we have more questions?
Hi, a quick question from me. Hi, I'm Hong Shin. Hi, great talk. A very interesting concept. I'm wondering about the implications that you know, the new sort of ideas of the multiple mechanisms that is possible that drive such observations that's pointing towards active or at least some sort of deep water formation in the Labrador and the Mingo Sea in LGM and HS1. Do you at this point of the research have some implications towards the strength of the overall AMOC with this addition sort of revealing new idea on the deep water formation in the north?
We don't have it from this data set, right? So my original idea, which I also published in the paper, was that it probably was more sluggish and less strong, but still it was there. And if you have a go to the picture, if you have a less export from the northward line, the southward export, you would also increase your vertical mixing. Like you would increase the mixing here, and the water would stay longer, and thereby it could take up more heat. That was one of my original ideas. We have some new data. Maybe Haug is from Finn Zufke, who has some data from this area, which looks like relatively stable export, but it's unpublished. So
okay,
and it's platinum thorium data, but he's about to publish it. So
okay, yeah, cool. Cheers.
Yeah.
So I'll wait and see.
Yeah, I think it's entirely very, very interesting to see this. And as if I wouldn't have seen the data of Finn, I would say, well, it's probably weaker. You had more diabetic warming, but seeing that data, it might be a slightly different picture. But
okay,
we'll see.
Cool, thanks.
Okay, if there are no more questions, then we will thank Janne again, and yeah, and thank you very much for attending the webinar, and we look forward to see you in the next webinar.